In this video, we're going to be looking at some more of the details of Cisco Express Forwarding, which is a fundamental component that allows our switches to look up and route packets without interrupting the CPU, without bothering the CPU from doing the very critical background management tasks that it needs to do. So, whether we're talking about routers or switches, both routers and switches do switching. Now, we don't normally think of routers as doing switching, but the process of actually taking a packet from one ingress interface and sending it out another egress interface, that is called switching. So let's focus on routers for just a moment. So routers have three ways they can do switching. Actually, historically, there are even more than this, but the three main ways that the CCNP are going to want you to know about are what's called process-based switching, fast switching, and Cisco Express Forwarding. Let's start with process-based switching. Back in the early days of routers, when a packet came in a router, the only way the router could inspect that packet and do what it needed to do was the CPU would have to be interrupted. So the CPU may have been busy doing an EIGRP routing update, or maybe it was monitoring the environmental status of the router, how hot is it right now. It could have been doing any number of things, but the CPU would have to invoke a process in the processor. We call this the IP input process. So if I, on a router or a switch, for example here I'll go to a router, if I'm wondering, okay, well, this process called IP input, how frequently has it occurred in my device? If I do show processes CPU, I will see all the things that my CPU has to do in this device, most of which will probably be completely meaningless to you. Chunk manager, what's that? What the heck does that mean? We have no idea. Check heaps sounds kind of nasty, but there's a lot of stuff in here. We have no idea what it is, but each one of these is something that takes a tiny slice of time, a tiny piece of attention from the central processing unit, the CPU of my router. And in here it's going to tell you for each one of these things, in the last 5 seconds, in the last minute, in the last 5 minutes, what percentage of the CPU's brain has been invoked to do this particular process. Some of these actually are pretty clear. Arp input. There's some ATM processes if you're actually doing ATM. And what we're looking for in here, and there's going to be several screens of this, somewhere in here there's going to be a process called the IP input process. Here it is, IP input. So this tells you, in this particular device, the process of interrupting the CPU so it could go into the routing table and look up a packet has been pretty minimal. It's been less than one per, it's been basically nothing. So if back in the early days of routers, this process was the process that was invoked to look up a packet. And so you'd see a non-zero number here. You might see a pretty high number. If my router was receiving tons of traffic and it was really, really busy looking up those packets, and the CPU was the one that was doing that, IP input process would not be zero. You might see 30%, 40%. So that's what's called process-based switching. And you don't really want to see that. Nowadays, routers and switches ideally should not do process-based switching. So how else do they do it? Well, then Cisco came along and they developed something called fast switching. They said, here's what we're going to do. We're going to set aside a separate little memory table that some hardware on the interface has access to. And when a frame comes in, we're going to look in that table. We're going to call that the fast switching cache. Now, the way fast switching worked was that when a packet came in, the router would say, okay, if I've never seen this destination before, this packet's going to 70.111. Well, if nobody's ever needed to go there before, the fast switching cache would be empty. It wouldn't have any entry that matched that. So that first packet would have to go to the router, to the CPU, to the IP input process. And in the process of looking that up by going into the routing table and finding a match and then sending the packet out, that would populate the fast switching cache with an entry. So the next time a packet came in for that same destination, now we'd have an entry in the fast switching cache. We wouldn't have to bother, we wouldn't have to invoke the IP input process, and we could route/switch that packet through the router much more quickly without really bothering the CPU to do it. But notice the key thing that I said there. A packet first had to come in for that destination. That first packet would have to be looked up by the CPU, and then that would be the event, the trigger, that would cause an entry to be populated into the fast switching cache. And those cached entries would age out after a while. You know, if nobody was sending packets to 70.1111 after a certain period of time, it would age out. And so a few hours or a few days later, if another packet came into 70.111, guess what? That would have to be looked up by the CPU and repopulate that entry. And those entries didn't track the routing table all that well. So if a routing entry went away, if all of a sudden we lost our route to the 70 network, it might take a little bit of time for that cached entry to vanish. So it didn't really track the state of the routing table. And if the routing table learned of a new route, if all of a sudden, oh, my routing table has learned about a new OSPF route to the 90 network, well, if nobody was currently sending packets to the 90 network, there wouldn't be anything in my fast switching cache. So then the developers at Cisco, they said, you know what? We should build a type of cache that's pre-populated. Basically, that whenever the router learns about anything, if he learns about a new route, if he ARPs for something and he learns about a new ARP entry, we want that to be pre-downloaded to a cache so that as packets come in, we don't have to send them to the CPU at all. The cache will already have stuff ready and waiting for them to use. And that was the whole idea behind Cisco Express Forwarding. Cisco Express Forwarding says, let's build what's called a topology-driven cache. You see, fast switching says, we're going to build this cache as it's needed, as packets come in. But that requires the first packet in every new flow to be punted to the CPU. Cisco Express Forwarding says, let's not do that. As my routing table is populated, let's download all that stuff to a cache. As my ARP table is populated, let's download all that stuff to a cache so it's ready, waiting to be used, and we never have to bother the CPU with stuff. So Cisco Express Forwarding is much more efficient at packet handling. So to understand Cisco Express Forwarding, we have to understand the types of tables that it uses, how those tables are populated, and what their names are. So there's two primary tables you need to be aware of for Cisco Express Forwarding. The first one is what's called the Forwarding Information Base, or the FIB table. So the Forwarding Information Base is sort of like a copy of the IP routing table, but it doesn't have everything that the IP routing table has. Let's think about this for a second. When a packet comes into the router and needs to be routed to an outbound subnet and an outbound interface, there's certainly stuff in the routing table that's critical to do that, such as the prefix, the mask, and the outgoing interface or the next hop. But there's also stuff related to that route in the routing table that really we don't need as far as packet forwarding. For example, the administrative distance of how that route was learned. We don't really need that as far as forwarding a packet. The metric, like the OSPF cost or the EIGRP distance, that's useful for the routing, but it's not, for the routing protocol. But we don't really need that for routing packets. So, route tags that show up in the routing table. There's a lot of extraneous stuff in there that our routing protocols need to select best routes, but we don't actually need for forwarding of packets. So the FIB table says, look, I'm just going to take the absolute crucial information such as the prefix, the mask, the next hop, and the outgoing interface, and I will populate that in my forwarding information base. But all that other extraneous stuff like metric and administrative distance and the age of the route, how long it's been since we learned it. I'm not going to put that in the fib table because I don't need that to actually forward packets. So sometimes we say that the fib table is sort of like a shadow copy of the routing table. You know, a shadow shows you your general outline, but doesn't give you all the same details as if I was looking directly at you, right? Same general idea here. And the fib is exactly matching the state of the routing table. So what I mean by that is, if I'm doing some sort of routing protocol, and it doesn't matter what it is, if my routing protocol learns of a new route, all of a sudden it learns of the 70.70 network /16. The moment that's put into the routing table, it's copied down into the Ceph fib table. If a route goes away, for whatever reason, it's poisoned or I lost my neighbor, whatever, if the 70.70 network disappears from the routing table, it's automatically pulled out of the fib table. So the fib table is tracking everything that's in the routing table. And whatever happens to the routing table, it happens in the fib table as well. Now, one also thing that makes the fib table a little bit different than the routing table is that, well, for example, let's take a look here. In a router, let's see here, do I have any IP addresses on this guy? No, I don't. Okay, so let's go to router 18 here for a moment. And to start things off, I'm going to go to my topology diagram. And I'm going to put this IP address on him. So I'll give him that IP address. No shut. All right, and let's see here. Okay, his link came up. That's good. All right. Now, switches are always running Cisco Express forwarding. Routers, sometimes they have it on, sometimes they don't. So real quick and easy way to figure that out. Show IP Ceph. The fact that I see anything here tells me that Ceph is turned on. For example, if I did no IP Ceph, turned it off, and now I did that same command, it would say Ceph not running. Pretty clear. So let's turn it back on, IP Ceph, and issue my show command. And let's see if we can get show IP route. Show IP interface brief. Ah, okay, my interface is up down. That's why I don't have anything for this. So going back to here, that interface is connecting to 0/4 on my switch. So I need to go to my switch real quickly and do whatever I need to do to get that interface up. I'll just do that for now. Okay, so now my router changed state to up. Okay, great. So here in my routing table, you'll see I've got a directly connected route to that prefix, to whatever the subnet is on that interface. When I do show IP Ceph, that prefix was automatically downloaded to my Ceph table. But look what else was downloaded. The host route, so the fib table also contains an entry for the exact 32-bit IP address that's on my interface, and some other things as well. It said, look, here is the subnet broadcast address. If anybody ever sends a broadcast to this subnet, the fib table has that. It says receive, which means I'm going to receive it on my CPU. I'm going to process it locally. If anybody ever sends, well, this is kind of a weird broadcast, but if anybody ever sends a broadcast to 18.19.18.0, that /32-bit entry will also be received and processed. So the point I'm trying to make here is that the fib table actually contains a little bit more specific information than the routing table does. The routing table just had the prefix. The fib table has the prefix as well as all sorts of specific information related to that prefix. And I can drill down a little bit more deeper. I could say show IPsec 18.19.18.19 /32 detail. Oh, it probably wants it as a dotted decimal subnet mask. Oh, it's because I'm not .19, I am .18. So you don't get a lot more detail in this particular case. It's just verifying that that host entry does exist, and it says receive, which means if I ever get any packets that match that /32, I'm going to process it locally on my processor. So that's that's one of the tables you need to be aware of, the fib table, forwarding information base. For the purposes of the exam, you should know what fib means. You should know it's a critical component of Ceph. You should know it matches the state of the routing table. So any prefixes that are in the routing table automatically get copied to the fib table. And if those prefixes are removed from the routing table, they automatically go away from the fib table. You should also know that the fib table contains more specific entries as well, like /32 host entries are in the fib table, whereas they're not necessarily in the routing table. So I said that there's two primary tables that Ceph uses. That's one of them, the fib table. The other one you're going to want to be aware of is what's called the adjacency table. So this is populated, as it says, with layer 2 adjacency information, such as, okay, my routing table might have a 32-bit entry for a host I'm connected to, but it's not necessarily going to know what the MAC address is of that host. Or if that host is reachable via frame relay, it's not necessarily going to know what the frame relay delc is I used to get to that host. The adjacency table is going to provide that information. So as we can see here, the layer 2 adjacency table is populated by your ARP table entries, your frame relay mapping entries. If you're running ATM, your ATM layer 2 information. And we can see that by doing the show adjacency command. So let's do something here. So what I'm going to do is I'm going to go to my switch now. This guy's connected to switch 3. And I'm going to put these two interfaces right here, 04 and 05, into VLAN 2. Actually, let's just say VLAN 18. And then I'm going to go onto my switch and I'm going to create interface VLAN 18 with 18.19.18.3 as his IP address. VLAN 18, okay. Interface range, fast Ethernet 0/4 through 5. Switch port mode, access. Switch port access VLAN 18. No shut. Okay, now let's create an interface VLAN 18. IP address 18.19.18.3. Okay. Now I'm going to go back to my router. Well, let's just stay on the switch. And I'm going to do show IPsef. Now notice it says here IPv4 Ceph is not running. It's a little bit misleading because Ceph really is running in the background to populate our ASICs and our TCAMs and stuff. I'm just going to turn it on right here. In the switch, it's IPsef distributed. Okay, so show IPsef. All right, so same thing. I now see my directly connected route because my routing table has it. I see my own host address. Now, from this switch, show ARP. Right now, all I know about is myself. So if I ping router 18, in the background, that's going to create an ARP request. And when he gets the ARP reply, there it is. So now I've got an ARP entry for my directly connected neighbor. And this ARP entry should have populated my adjacency table for Ceph, which is viewable via show adjacency. And let's just see what happens if I just hit enter. There it says, I have an adjacency. VLAN 8, so my VLAN 18 layer 3 interface has learned of this adjacency right here. Let's see if I can get a little bit more detail. Show adjacency VLAN 18. Same output as before. Detail. Now I get a lot more information. Show adjacency detail. In this case, you say, well, why didn't you type in the physical interface? You know, why didn't I type in show adjacency fast Ethernet 0/14? Because it was his layer 3 interface VLAN 18 that created the ARP request, that did the whole ARP process. So this was bound to his layer 3 interface, not his physical port. And we can see here, here's the adjacency information of my peer, my directly connected neighbor. And we can see it says, okay, well, if I ever need to send any information to that neighbor, let's parse through this here. If I go to router 18 and do show interface fast Ethernet 00, notice his MAC address begins with A40C and ends with 749C. So A40C, 749C. And here it is, A40C ending with 749C. So that is the MAC address I'm going to use to rewrite if I ever need to send any Ethernet frames to that neighbor. And what's this stuff right here? Well, if I do show interface VLAN 18, that is the MAC address of my switched virtual interface. And this is the type code. 0x800 is for IP. So if I ever need to if I ever get any incoming packets that need to be routed to this guy, my adjacency table contains all of my layer 2 rewrite information. So if a packet ever comes in for 18.19.18.18 show IPsef, I have a 32-bit entry now that says attached. That will cause us to look in the adjacency table where I will find this information for the rewriting of that packet. So you can see the moral of this story is Ceph uses the fib table and the adjacency table together. The fib table says, do I have an entry for this? So as a packet comes in, do I have an entry for this host? So if a packet comes in, let's take a look at another example. Let's walk through this a little bit more. So let's say an incoming packet comes in here, and the destination is equal to 20.20, let's say 11.11.11.1. That's the destination. So the first thing that's going to be checked inside our router or switch, any device doing Ceph, is going to be the fib table. And he's going to look to see if he has any entry that even closely resembles this. Just like we do a routing lookup, it's no different. We're looking up to see if we have something in here. Now, if there's nothing that even closely resembles this, same thing happens as if we didn't have a route that resembled this. We destroy the packet, we drop it. Now let's say this is what I have. Let's say the 11 network, let's do a couple of things here. Let's say first of all it resides right here. And .1 is directly connected to me. All right, well if I'm directly connected to it, that means I already had some layer 3 knowledge of this. Either I had it configured right here. Option number 1 is I did the no switch port command, and then I put my IP address right here. So if this is what I did, well, that populated a connected route in my routing table for 11.11.11.0. That pre-populated a fib entry. Okay. So now when this packet comes in, if I never had spoken to 11.11.11. Let's put it as 3. Okay, so if this was all I had, because I've never actually, 3, this is .1, this is .3, getting my IP addressing confused here. .3 is right here. So this is not for me, this is for the router. Okay, so it's going to this guy. So in my fib table I'd have the entry for the subnet. I'd also have an entry for myself. That's for me. And let's say this is all I had. Well, when this packet comes in, it's going to say, well, it doesn't match this. It does match that entry. That's the most specific entry I have. And we're going to see here in just a second in the upcoming slides, it would say, well, there's a little special indicator in here that says if this is all that I match, we need to ARP for whoever this guy's trying to talk to. So that would kick out an ARP request. That would trigger that. The ARP reply would come back. And so now the ARP reply would populate an entry here, which would say, I'm attached to that guy. And in my adjacency table, we now have a layer 2 adjacency for 11.11.11.1, and it would have the MAC address of whatever that is, BB. So now when we have this information, now we've got enough information to match it on this entry right here. And between the combination of that and this, we have enough information now to direct that packet out this interface. we can rewrite the packet and send it out right here. So once again, to recap, the moment this switch or router, doesn't matter what it is, switch or router learned of this subnet because I was directly connected to it, that populated these two entries right here in the fib table. An entry for the subnet, because we learned about that in the routing table, and a receive entry for my host address in that subnet, which is me, the switch or router's interface. We'll just say switch in this case. Now when a packet came in for somebody on that subnet, like this guy right here, .1, if I didn't previously already know about him, the only entry that matched was the less specific one right here, and that triggered an ARP in my device. So my device then said, okay, well, I'm directly connected to that. I'm going to ARP for it. When the ARP reply came back, that populated an entry in my adjacency table. So now I had everything I needed to forward the packet out. So the takeaway from this is the combination of the fib and the adjacency tables that are used to forward frames and packets. They're used to route our frames and packets and to rewrite the layer 2 information in those frames as we send them out. All right, so let's go into a little bit more detail of this. Now there's some adjacency types that cannot be Ceph switched and either must be dropped or sent to the CPU for processing. For example, you might see the names of these things in the exam. Definitely the two that you should be familiar with are the glean and the punt adjacency. They both basically mean the same thing. If you see an adjacency type that says glean or punt, that means we need to forward the packet that matches this to the CPU for further inspection, for further processing. So a glean adjacency means I need to wait for an ARP. We need to trigger an ARP, and we need to wait for an ARP reply. So going back to this right here, when this packet first came in for 11.11.11.1, the only thing that we somewhat matched was this right here in the fib table. So what happened was, as a result of this packet coming in, we created an adjacency for 11.11.11.1, and initially it was marked as glean. Why? Well, because we didn't have all the information for this yet. We didn't know the MAC address. We didn't know the outgoing interface. So this created an entry called glean, which meant, okay, I need to take this packet and process it in my CPU and send an ARP. So a glean adjacency means somebody's asking for this, but I don't have all the layer 2 information just yet. So my switch needs to take some action, like send an ARP, to finish off the process. Now, if something happened where, let's say that this guy didn't reply back, he didn't exist, it would just stay as a glean adjacency. It'd mean, okay, well, I never got a reply back to my ARP. Eventually it would be aged out, but it would just stay as glean. So we don't want to see it as glean for too long. Hopefully it'll only stay as a glean adjacency for like a second, as long as it takes to send out the ARP request, get the ARP reply back, and now we can change this flag from glean to what it really should be, attached with the various information that we learned. So glean is just supposed to be a temporary state. Shouldn't be there for too long. Just means let's ARP for it, get the ARP information back, and then we can change it to an attached adjacency. Let's just go down the list here of some of these other ones. Null, that means that it's a valid packet, but we need to drop it. To think of an example of when you might see that. Well, if I went into my router or my switch and I did this, let's say so here I'm creating a host route, but I'm saying if you ever get any packets for this particular host, send them to null 0. Well, that means basically kill that packet, put it into a black hole and discard it. That's probably going to create a null adjacency. I hope. I haven't actually tried this before. Let's see if it actually worked. Show adjacency 18.19, 18.5. Let's see if we can put that in there. 18.19.18.5. There's nothing there. I think it actually did create a null adjacency. It's just not showing it right here. I just don't know of any way to actually display that right now. But an adjacency in the adjacency table, the takeaway from this is if it has a flag of null, that means this packet goes nowhere. We're going to drop it in hardware. We're not going to bother the CPU with it. Ceph is going to drop it in hardware. If an adjacency entry has a flag of drop next to it, same thing as null. That means we're going to drop it. But typically that means we're going to drop it because the adjacency recognizes that there's something bad here. Like, for example, if a packet came in and we instantly recognize that, this packet, the encapsulation is bad. There's something wrong with it. Or maybe a packet comes in and it's for a route that we don't have. Packet came in for the 707011 host, but we don't even have a route to 7070 anything. Well, that might create a drop adjacency, meaning we don't have a route for it. A discard adjacency, that's typically created because we've got some sort of security policy like an access list that says drop anything matching this. So if I have a security policy that says drop any packets going to 90.90.77, that would create a drop adjacency for that particular host. And punt adjacency, that's very similar to glean. Glean and punt both have the same effect. That means we have to take this packet and forward it to the processor. What's a little bit different is glean specifically means I need to resolve the layer 2 for this. I need to send out an Arp request. That's really what glean means. Punt is for if something comes in that specifically needs to be process switched because it's specifically for our processor. For example, let's say I'm doing EIGRP. My switch, my router, is doing EIGRP with an EIGRP peer. Okay, well, if that EIGRP peer sends me anything, whether it's a hello packet or an EIGRP update, that should be sent to the multicast address of 224.00.10. Well, there should be a punt adjacency for 224.00.10. In my adjacency table, there should be an entry for that specific /32 that says, if you ever receive anything matching 224.00.2, punt it to the CPU. Because the CPU needs to see it. It needs to recognize that hello or that routing update. So anytime you can think of, okay, what are examples of things that have to go to my routing processor because my routing processor has to see them. Whatever they are, that would create a punt adjacency. Now, I don't think the CCNP is ever going to expect you to know all those details I just gave you. But what it will expect you to know is that there's some adjacency types that will force a packet to go to the CPU for further processing. So on multi-layer switches, Ceph is going to be enabled by default. And why is that? Well, to go back to my whiteboard right here, this one, in order for these layer 2 tables, specifically this layer 3 table right here, let me just put a couple of big circles around it. In order for this table to be populated, this TCAM memory, we'll talk more about TCAM memory in a second. In order for this to be populated, Ceph is the thing that's responsible for populating it. What's in this table directly came as a result of what's in the fib table. If there was no fib table, this couldn't be populated. Well, when you turn on a switch, Ceph is automatically running in the background and populating this with information. So even though in my switch you might say, but wait a second, Keith, when you went into the switch it said Ceph is not running. It's a little confusing because the moment I turned on the switch, it started populating this table with entries, even if I didn't have any switch virtual interfaces. Even if I went into a switch and I said, let's just think about a switch that's turned on by default. It's got no VLANs but VLAN 1. All it has is interface VLAN 1, but there's no IP address on there. Guess what? That layer 3 table, from the moment you turn on that switch with a default configuration, is going to have stuff in it. It might have an entry that says anything that matches 255, 255, 255, 255, punt that to the CPU. Anything that matches multicast addresses beginning with 224, it's going to have some very generic entries, but it will have entries in there, because Ceph was running in the background to populate that. That's the best that I can explain that. And there's just some packet types that can't be Ceph switched because of their very nature. Arp requests. Certainly if the switch itself needs to create an Arp request, that can't be Ceph switched. This processor has to be involved in the creation of an Arp request so it can see the Arp reply that comes back. Packets that naturally require a response from the router's CPU. For example, if a packet comes in that needs to be routed and the TTL on that incoming packet is 1, well, the router would have to see that because he's going to decrement it to 0. He has to be able to kill that packet, and that would cause a TTL expired or a TTL exceeded message, so that has to have visibility to the CPU. If a frame comes in and the MTU is too large, that has to be visible to the CPU. If a packet comes in and some sort of fragmentation needs to take place, that has to go to the CPU for processing, so the CPU can fragment packets. There's no way to fragment packets in hardware. If fragmentation needs to take place, that's a CPU process that has to do that. If an IP packet comes in and your forwarding engines recognize that there's IP options in the IP header, you don't normally see that, but if there's any IP options in the IP header, guess what? We got to send that to the CPU for processing. Ceph can't deal with IP options. We can also see here routing protocol traffic. If your routing processor is running any routing protocol, BGP, EIGRP, whatever, those packets always have to go to the routing processor to be handled. And we can also see CDP and any packets that need encryption. So those are all examples of packets that need to go to the CPU. But when you think about the mass quantity of traffic that's going into a router or into a switch, all of this stuff here is a very small percentage of the overall traffic that your router or your switch is handling. So the vast majority of stuff that your router switch is seeing can be handled by Ceph. Very little of it actually needs to go to the CPU for processing. Okay, so let's just talk about Ceph one more time and how it relates specifically to switches. It's really critical to your understanding of switches. So imagine for a moment that this large box represents my switch's chassis. And I already mentioned in the previous video that when packets come in, there's a specialized piece of hardware called an ASIC. We're going to get more into that in this next video, that we call the forwarding engine. Now, some switches have a single ASIC as their forwarding engine. That one ASIC is able to look up layer 2 information, layer 3 information, look up security policies that you've implemented. Other switches have multiple different ASICs, actual chips, performing each distinct function. For example, like on the Catalyst 6500 switch from Cisco, there's multiple ASICs. You've got one ASIC just doing your layer 2 lookups, another ASIC just doing your layer 3/4 lookups, another one just looking for security stuff. But in other switches, like your 3750s, for example, you might just have one ASIC doing all those lookups. Now, when the ASIC is looking stuff up, first of all, why did they design an ASIC in the first place? Because an ASIC is a piece of hardware with millions of little tiny microscopic transistors in it, and the way they created it was that so it's specially designed to look up stuff. It's designed for that purpose. And ASICs can look up things far faster than a processor can, than a CPU can. So that's why they're designed to speed up this process. Because really, when you think about it, in a switch and in a router, the processor's main job is really designed to keep everything up and running, to do all of your background tasks. The processor does routing really well, routing protocols, forming neighbor relationships, doing dual or the link state algorithm or the SPF or whatever. In switches, the processors can do that. They're also really well designed for doing spanning tree and CDP, all this stuff that keeps your network nice and stable so it can be used for packets. You don't really want to forward your packets to that processor because the time that processor is spending on looking up your frame is time he could be spending on other important stuff. So switches said, look, let's design some hardware to offload the processor. So we've got our forwarding engine. I'll just write that right here. And in this particular case, I'm just going to say we have a single forwarding engine. So when a frame comes in, it's this piece of hardware, this little chip that looks up the frame. Now, where does he look it up? Basically, what the forwarding engine does is he temporarily stores that frame in memory, and he extracts some critical pieces of it. You see, this forwarding engine, when it was designed to know what an Ethernet frame looks like. It was designed to know, okay, I need to go right here and copy out of this the source and destination MAC addresses. I need to go right here and copy out of that source and destination IP addresses. So it knows in all these, because remember, a frame, let's say a 1500 byte Ethernet frame. It's 1,500 bytes. Well, if we multiply that times 8, that's what, like 9,600 bits? So these 9,600 bits that make up one frame, this ASIC is smart enough to know I go right here for this part I'm looking for, right here for this part I'm looking for. And so now he's got these, what we call search keys. That's what we call it, the search key. This is what I've extracted here. This is what I need to look up. Now, where does he go to see if I have something that matches this MAC address, that matches this IP address that I pulled out of this frame? Well, that's where he goes into special memory called TCAM memory. I'll talk a little bit more about that coming up. Now, just like a particular switch might have one or more forwarding engines, it might have one or more TCAM memories as well. Taking it back to, for example, the Catalyst 6500 or 7600 platforms. Multiple TCAMs. There's a specific TCAM memory chip just for your layer 3 routes. There's another TCAM memory chip just for all of your security stuff. Whenever you configure your access lists or your VACLs or your private VLANs, all that's put right in there. There's another TCAM memory just for quality of service. But other platforms like the 3750 and the 3500s have just one TCAM chip. They say, okay, of this memory right here, this portion of it's going to be for my routes, this portion is going to be for my security, so it just depends. Sorry, I got a little frog in my throat here. So let's say that we've got, just to make it simple in this case, let's say we've got 2 TCAMs. And this one on the left has my layer 3 information. Actually, let's just do 1 TCAM right now. Make it even simpler. So here is my TCAM memory, my L3/L4 TCAM. I'll say TCAM memory is kind of redundant because TCAM stands for ternary content addressable memory. So it's like saying ternary content addressable memory. So I'll just say TCAM. And within here, it sort of subdivides this into 2 sections. And I'll get to that in just a second. So if this forwarding engine, when a frame comes in, says, okay, I'm going to extract the IP addresses from here so I can see if it needs to be routed, and if it does, where to send it. He's going to go into this TCAM. He's going to do this like in microseconds. Now, where does Ceph come into play for all this? Ceph is the process that's responsible for programming this. Actually, Ceph doesn't program this. Ceph is responsible for providing the information that's going to go in here. So let's say that up here in the upper right, I've got my RP, my route processor. This is a CPU. And he's the one that's learning everything as far as layer 3. He's the one that's doing Arp requests, processing the replies. He's the one that's forming EIGRP and OSPF neighbor relationships. It's learning of routes and putting them in routing tables. So we've got right here the 2 primary tables that he's responsible for. Of course, he's responsible for a lot more than that, but we've got the IP routing table, and we got the ARP table. As his job, as he learns things, to populate these 2 tables. Now, if I have Ceph as a process running on this processor, then he also knows, okay, I have to create 2 more tables. Whatever I learn here in the IP routing table, most of it, not all of it, like the metrics and administrative distance, we can leave that behind, but the basic stuff goes here into the forwarding information base. And whatever I learned here in the ARP table and maybe my frame relay map table and other things goes here into my adjacency table. Now here's where all this merges together, how it works off each other. There is a process, you don't need to know the name of it or where it is or anything, that when this is happening in a switch like this says, okay, as stuff is learned in the fib table, I'm going to copy that right here to this portion of my layer 3, layer 4 TCAM. And as stuff is learned in the adjacency table, I'm going to copy it right here and put it into that. So it's not actually the Ceph process that's copying it in here. Ceph is just creating these tables and providing the information. And then there's something else that gets invoked in the background that's sort of watching these tables like a hawk. And whenever it sees a change, it says, aha, I need to make that change reflect down here in TCAM. So your layer 3, layer 4 TCAM is exactly replicating the state of your fib and adjacency tables. And your fib and adjacency tables are monitoring the state of your IP routing table and predominantly your ARP table. So that's why Ceph is so critical in a switch, because if we didn't have these tables right here, there'd be nothing to put in our TCAMs. And if there was nothing to put in the TCAM, that meant that every packet that came in would be forced to go to the routing processor for lookup, which would really slow it down. So that's the basics of Ceph. That you've got the fib table, the adjacency table. Fib table is for your layer 3 information. adjacency table is for the layer 2 information. What's the MAC address that goes with that IP address? What's the outbound interface that goes with that? Is that something that we necessarily have to send to the RP because he needs to see it? Or is it something that we can bypass the RP? All of that's in the adjacency table. So hopefully that helped clarify sort of the really important role that Cisco Express forwarding plays in a switch.